All right, let's start for real. Well, this whole thing started as an F# Advent project. And F# Advent calendar is something where it's a nice F# project where people sign up for specific dates before Christmas. And if you sign up for a specific date, you have to publish a blog post about F# on that specific date. And I signed up for day, just I think about 15th of December. And when I was thinking, well, what should I do? I was thinking, well, maybe something Christmassy or Star Wars, because this was like 2 days before the premiere. So I went for Star Wars, as you can see. And because it has to be in F#, I was thinking, well, what kind of data can I analyze with F#? And I decided to model the Star Wars social network using the script files. So this is a screenplay of one of the episodes. And they're actually quite easy to parse because they have very strict structure. And they're all available online. So this was like the perfect data source. So the normal script files, usually they have title of the scene, which always starts with int dot or ext dot, meaning interior or exterior. And that's the beginning of the scene. And then they have some description, what the camera sees when the scene starts. And then they have the people that are actually talking in the scenes, in bold, always in capitals, in the middle of the file, actually. So that seems to be quite easy to parse. And all the data were available online. This is a page from IMSDB, something like the Internet Movie Database, but this is the script database. I'm not sure what's the legal status of this, because they publish usually scripts very early after the release, but they make it all available online. So I decided, well, let's just download all the scripts and parse them. And then we can model social network by looking at which characters actually speak together within the same scene. And that gives me roughly the idea which characters know each other. If they speak in the same scene, that probably means they speak together. And that means they interact, they know each other. So this is a nice approximation of the actual social network. So I looked at this website, I looked at the source code, and it's quite straightforward. It's nice HTML, where always the scene is in bold, and then all the people are in bold. So that's relatively easy to parse, right, in theory. So this is exactly the same part of the script I was showing before. So now we have, again, the scene title, some description, and then the name of the person who's speaking. And this is the F# code that I wrote for this. I was actually using something called from F# data. It has a very nice HTML type provider, which also includes an HTML parser. So I could actually just load in the HTML document. I'll try to use this. So this is the URL of the first episode. I could load it into the HTML document, and then take all the descendants of this specific tag. And because the scripts were pre-formatted, they were always in this tag. And then I could just extract all the bold items by taking the B elements. That's straightforward, right? That should give me all the titles and all the names. And then I just took the inner text. So this is the whole HTML parser. So it's relatively easy to use. And the first iteration of my source code, actually, I was trying to finish it on time before the premiere, before I was supposed to publish it on the F# Advent website. So it had a lot of code, a lot of different parsers for different parts of the scripts, and a lot of regular expressions. And I guess it's not only me, but I don't find regular expressions particularly readable. So for me, they're just write only. So when I looked at it again, when I wanted to incorporate the new episode into the analysis, I was like, what was I doing here? Like, what is this actually matching? So I rewrote the parser. And now this is probably the most F# code you'll see here. And this is using, well, the functional way of writing a parser is to just split your document into elements and then go through them recursively. And if you have different sections in there, you just accumulate what's in the section and then return it in form of basically a recursive function. So this is a recursive function that takes all the items in my script, and then it goes through each item. And wouldn't it be nice if you could do something like, if it's a scene title, then just give me the title of the scene and parse characters that are in the scene. And if it's a name, then just give me the name and go on, parse the names until we get to a scene title again. And if it's something else, then just go on and skip it. So this is what it actually does. I have two accumulators, one for scenes and one for characters. And the scenes are basically just lists of characters that speak within each scene. And then I could get the social network by looking at which characters speak together. So here I'm just going through the elements. If it's a title, then I'm returning the characters that speak in the scene, because it means that the scene ended. And if it's a name, then I'm just adding it into the accumulator. And this is possible to do because of something called active patterns in F#. And if you have been to Jan Kuij's talk yesterday, I think he was talking about active patterns as well, because they are really, really useful for writing parsers like this. If you have a very small thing you want to model, then active patterns are the way to go. So I basically put all my ugly irregular expressions inside this little function that takes some text as an input. And then if the text matches the scene pattern, then it returns the scene title. And if it matches the name pattern, then it returns it as a name. And otherwise, it's just some random word. And then I can just pattern match over it. So this is very readable. I can see what's happening here. I'm just matching with a title, with a name. And all the complexity is hidden within this little function. And I don't have to look at this regular expression again. The problem with names in Star Wars is that they have a lot of characters. They have dashes, they have slashes, they have numbers, they have spaces as well. So something like C-3PO, it has a dash, it has a number, so it's not like a normal name. So this is the reason why this has to be so ugly. So the takeout message is that active patterns are very good for hiding the complexity behind the readable code. So I can just look at the pattern matching, and it's very, very readable, and you can see what's happening there. But this all sounds very nice, right? Well, it's never this nice. Well, you can't really see this. Because I looked at some of the other script files, and turns out they don't respect the proper format for a script. So here you can see that here is Jar Jar speaking, and he's not in bold, and it's just in capitals followed by colon. So it's completely different format. So it turns out some of the scripts use the standard format for scripts, some use slightly different ones. So I had to add another parser, another regular expression, things like that. And you would think that this is all nice, but then I looked at what my parser actually extracted, and R2D2 wasn't there at all. So what was actually happening? I looked into the script files and found out that he doesn't speak there at all. The scripts always say, like, R2 frantically beeps, or, yeah, beeps provocatively. And it wasn't the only character. Like, Chewbacca doesn't speak in the scripts at all. So kudos for the actor who could actually put more expression into it. But in the scripts, it's just Chewbacca barks a command, and Han replies, boy, you said it. Well, you didn't. So this led me to a very complex mathematics. So don't be scared, this is just an equation. Well, what I actually decided to do was to estimate, for these characters that don't speak, to estimate how many times they would probably speak if they spoke. Which means I looked at the number of times each character is mentioned in the script, and how many times each character actually speaks. And I use this to estimate weight that each character has. So this is weight of a character. It's basically just the average number of times a character is talking with someone else, divided by the number of times the character is mentioned in the script. And turns out, on average, this is about 1/2. So each character is mentioned about twice as much as the character speaks. And I use this to estimate connections between the non-speaking characters and the actual speaking characters. I added links for R2-D2, Chewbacca, and BB-8. Some characters were not happy that I didn't add them. Actually, I realized that there are so many characters that don't speak explicitly in the film. So I just decided, well, let's just not go into this. Let's just add the really important characters. And then some characters messed up my analysis again, because some characters, especially in the new episode, they are mentioned a lot, but they don't really speak. Yeah, so no spoilers, but some characters don't speak, but they get mentioned a lot. So I actually had to add another hack into it, and for each character, basically just decide which characters are similar and use them to estimate the rate of interactions. And then I was again looking at my results, and it still didn't really match. So this is part of the script. And I looked at this line, and my nice regular expression was just matching the name on Medon. So why? And actually, this is not I. This is lowercase l. I don't know if they created the scripts that they put on the internet by just running some OCR on the script, but this is lowercase l. So this is actually quite a lot of work. So how do I find out which characters are in Star Wars and which characters are actually honestly there and which ones are just mistakes in my parsing algorithm? So I was looking around the internet, and obviously there are things like the Wikipedia, which is Wikipedia for Star Wars. But there is also something called Swappi, which is the Star Wars API. So if you want to find out anything about characters or planets or anything like that about Star Wars, you can use this. And they have a lot of nice wrapper libraries. I looked at the website, and they had Python, JavaScript, Android, Java, and C#. So yeah, this is .NET. Maybe I could use it. Maybe I could. Wow. So if you are an F# programmer, if you are looking at JavaScript code, well, you feel like this. And then I decided, well, no, not really. Maybe I can write my own parser from F# and call the API from F#. Because what Swappi actually does, it returns. You send it a request, and it returns the response in a JSON format, which is quite nice and parsable. So this is part of the C# code, and you can see that it's quite long, and most of it is just calling get and set methods for each of the properties. So these are actually elements in the JSON document, so species, eye color, homeworld, etc. And the C# code had a lot of files like this for every specific thing you can get from the API. So I'm not saying this is wrong. This is the way to do it in C#, and most of the other languages looked very, very similar. But, well, let's try to do it in F#. And, well, let's first go to the Swappi website. And they have a very nice documentation with everything. So, for example, if we want to look at people, this is the site for people, and they have an example request here. So if we just copy that over, and here I'm using F# in Xamarin Studio, and I'll be using the F# JSON type provider, which is a very useful thing, as you will see. So let's just create a type using the example request they gave me on the website. So I just copied in the example request, and now all I can do is just create a variable called p, which will load the website. And let's create a function out of that. Let's create a function getPerson. And because they use IDs to get the actual results, I'm just giving it ID as an input. And let's just load the correct address. OK, now I have a function to get the person. And let's just run it in F# interactive, which is in this bottom part. And let's get one person here. Let p equals get person. Let's get the first one. And what it returned is the JSON document. And I don't want to go through all the trouble of looking at the example response, and they have the documentation for everything, but that's quite a lot of reading. So I'll just do p dot, and I have everything that's in the JSON document. So birth year is a string because it has some additional information. It's not years in our time. But for example, the height is an integer because it's just the number, how high the person is. It has a home world, it has the hair color, and it has a lot of other information, like a mass, it means the weight of the person, I think in kilograms. So what's the name? And it's Luke Skywalker. And does anyone know how tall Luke is? Let's have a look. 172 centimeters. So this is really fast. You can see that I got exactly the same code that I had in C# here. This is doing exactly the same thing that all this code is doing on basically just 2 lines. So actually yesterday, I apologized to some people who had a talk yesterday, but I decided, well, Swappi has many libraries here, but it's really missing an F# one. So what I did yesterday, I wrote it. Thank you. So you can see it on GitHub. It has some examples here. And if you look at the Swappi website, documentation, you scroll down, help libraries, F# here. So you can play with it yourself. And you can do all sorts of fun things with it, actually. So I have some examples here. I'll just load them. So do you think that Luke Skywalker is average-sized for a Star Wars character or not? So let's find out. So here in this piece of code, I'm just downloading the height of all characters that are in the database and averaging that. So the average, oh, I didn't load it. So get all people. This might take a while. But I think there are only about 87 people in the whole database. Now I have to wait till it finishes. Okay, still nothing. Let's hope the internet works for me. Yes, I have it. So now we can look at the average height of a Star Wars character. And it's 174. So yeah, Luke is pretty much average. And we can also look at which eye color is the most frequent among Star Wars characters. And the most frequent one is actually brown. So for example, Leia has brown eyes. Then blue, Luke Skywalker, etc. Did you know that Chewbacca has blue eyes? So very useful information. And then the third most common eye color for Star Wars character is yellow. So a lot of very useful information. So let's go on. So this is all nice, right? So what can we do after we actually extract all the information from the script? So now I actually had the list of characters. I knew which characters interact together in each scene. So that gave me a social network. So I used D3.js, which is a JavaScript library for visualizations, and it can do anything. The only problem is that for mere mortals like me, it's really hard. But if you go to the website, it has examples of so many visualizations. You just go through and pick the one you like and then tweak the code. So this is finally the social network of all 7 Star Wars movies put together. And because it's in D3, I can actually open the network and drag it around and play with it. And you can see quite a lot of interesting information even from this, because this part of the network, it's the prequels. You can see that there are a lot of nodes. They are very densely connected. These are the characters from the original trilogy, and this is the new one. So you can see that the new one didn't follow the trend from the original episode, from the prequels, because there are just so many characters. So for example, this black node is Darth Vader, and this is C-3PO, etc. So you can go online and play with this. And I wanted to highlight a few of the episodes. So this is the first episode from the prequels, The Phantom Menace. And you can see that there are many characters, quite a lot of minor ones, several bigger ones, and the network is very densely connected. And we can compare it with The New Hope, the original Star Wars movie, and there are almost no very small minor characters. Almost all of them are the major ones, and these guys are connected together, and the network is relatively small. And then let's compare this with The Force Awakens. And this network is slightly bigger, but still it doesn't have that many minor characters or that many connections as the prequels. And we can again play with this. For example, this is Poe, and this little pentagram of nodes are the Resistance pilots. So and so now we have all the networks. So can we actually get some more information out of that? So I do some things with network science. So I decided to look at some very basic indicators and find out who's actually important in the social network. So the first basic measure is a degree, which if you have this social network, a degree for a specific node is just the number of connections that node has to other nodes. So this guy has 6 connections, this guy has just 3 connections. So the assumption is that the more important someone is in the network, the higher the degree. And in terms of the story, this means that the higher degree means that the character talks to many other characters in the movie. And then the second measure is betweenness. That's a bit more important, or a bit more interesting measure in terms of the social network. Let's take this guy in the middle, and what betweenness measures is how important that specific node is to what's happening in the network around it. So this guy, for example, if these two orange guys want to talk to each other, they have to talk through the green guy, because they don't know each other directly. So the green guy is very important for connection between these two. But if we take these two guys, if they want to talk to each other, they can use two different paths between themselves. So the green guy is not that important, because if he disappears, then they can still talk to each other. So betweenness measures this. Formally, a betweenness of a node given to other nodes in the network is just the number of shortest paths between the two nodes that lead through the central node, divided by the total number of the shortest paths between the two nodes. So for this situation, there are two shortest paths between the orange nodes, and only one leads through the green guy. That means this situation has betweenness 1/2. And the betweenness for a node altogether is just sum over all different pairs of nodes in the network. So this is quite complicated, but if you use R, then you can just call the function called betweenness on a network. I wouldn't like to implement this, because I would actually have to implement the pathfinding algorithm to find the shortest path between all pairs of nodes. Well, this is very easy. But still, I'm using F#. And in F#, I can use something called R provider, which gives me access to all the R functions from F#. So I did basically the same thing. I just opened iGraph and called R dot, which opens the R provider, R dot betweenness on the network. And they gave me all the values. So how does it look in terms of the Star Wars social network, actually? Well, I put together a social network for all the prequels and for all the original trilogy. And in the original trilogy, the person who talks to most other people is Luke, which makes sense because he's supposed to be the central character. And in the prequels, the person who talks to most people is Anakin, which also makes sense because he is supposed to be the main character. But this is just degree, so I looked at betweenness. And for the original trilogy, it's basically the same people had high degree and high betweenness. That means the people talk to each other and they connect different communities. But in the prequels, do you see Anakin there? So the problem is with betweenness, if you want to interpret it in terms of the story, it means that, for example, if you have the dark side and the light side, and the guys between the dark side, they interact with each other, and in the light side, they interact with each other as well. And the nodes that actually interact with both of them, then they have high betweenness. But in the prequels, actually, Anakin sort of just drags along. I think here it seems that the Obi-Wan is the one who's driving, actually, the story, because he interacts with the different communities of people. But Anakin just isn't important to the story that much, it seems. And if you look at which characters are here, well, actually even Jar Jar is more important. So let's look at the Force Awakens. Actually, the people who interact with most people is Poe, which makes sense because he goes through a lot of different environments and talks to a lot of other characters. And in terms of betweenness, the most central character is Kylo Ren. And it sort of makes sense as well, because he is the character that sort of connects some characters from the original trilogy with the new trilogy. And he also talks to a lot of different people, which gives him the high betweenness. So it does make sense. Unfortunately, Rey is not very happy with this. But the reason is that she has basically her own story. During the story, she basically doesn't meet any of the resistant pilots, for example, whereas Poe does. So that gives her a quite small degree. She didn't even make it into the top 5, but higher betweenness, but still not that much. And we'll see in the next episode how that turns out. So, who is the most central in the whole Star Wars universe? Well, Before the new episode, the episode 7 came out, it was this guy, Obi-Wan Kenobi. After the episode 7 came out, I ran the algorithm again, and any guesses? Almost. It's C-3PO. Because it makes sense, he's in every episode. So this is the most central character in the Star Wars universe at the moment. And if you look at, now I was just looking at the individual characters. And we can look at the whole network as a whole, if that tells us something about the difference between the prequels and the new episodes. So again, I did several comparisons. The first one is the size, that means number of nodes in the network. And this is episode 1, this is episode 7. And you can see that episode 1 has the most characters. It means a lot of debates in the Galactic Senate. And then it goes steadily down. The original trilogy has less characters. And these are just characters that talk in at least 2 scenes. I discarded characters that appear just once. And I also discarded characters that are not specifically named. That means if someone is just called a stormtrooper or a technician, they are not in this network. And episode 7 has more characters again. And we can look at other measures as well. One of them is density of the network. So if you have this social network again, just compares how many links are in the network compared to how many there can be in theory. So this is just the proper equation for this. And density in a social network tells us how much the characters interact with each other. And the prequels, these are the first 3, have, well, at least the first 2 have the smallest density, which makes sense because there are so many characters, they just don't talk to each other very much. And these 5 episodes have higher density, which is, I think, it correlates a bit with the rating. And then the final thing I try to do is to look at the clustering coefficient of the network. And the clustering coefficient tells me, if I'm in a social network, if my friends know each other. If I know 2 people, do these 2 people know each other as well? So in terms of this network, if you look at this guy, he has 3 neighbors, and only 2 of them know each other, and this link is missing. And if you look at this guy, he has again 3 neighbors, but they all know each other. This is again how you compute it in terms of the equation. So it's just the average number of links between neighbors, whereas the maximum number of links between neighbors there can be. And this is slightly more complicated, but in terms of the story in the social network, it means that if one character just goes through the story and talks to various other people that don't know each other, then that character will have small clustering coefficient. And if it's about a group of people who interact with each other a lot, then the network will have high clustering coefficient. And in this case, it correlates with the quality, I think, because the prequels have the smallest clustering coefficient, and the later ones have higher. So this is something we have to say about the episode 7. It has a high clustering coefficient, which means it's much better than the prequels, actually. I am not really convinced that the clustering coefficient correlates well with quality in general, because I think some of the fairy tales have this structure where the main character just walks through the story and meets different beasts or other characters. But in this case, I think it definitely adds to the quality. And again, how do we compute this? Well, in R, I just call a function called graph density and transitivity, which is the clustering coefficient. And in F#, it's exactly the same. So because I'm a lazy programmer, I don't have to program everything. And all the plots I was showing, they were actually not screenshots. They were calling Google charts directly. So this is how I created the charts. I basically just opened the explode library, which is an F# library for charting. I took one of the measures, added a label and a value, and just passed it into chart.bar. And just to prove it to you, this is not static. It actually tells me what's the precise number and things like that. So this is a very useful thing to do if you want to embed some chart into a website. And another thing I did afterwards, I also tried to model it in Neo4j. At the end of my slides, there is a link to a demo project with the Star Wars social network in Neo4j, so you can play with that as well. And this is all nice, but we can use the same kind of things in real world. So for example, I was analyzing the social network around F# on Twitter, and this is the visualization, so you can see it's much bigger than the Star Wars social network. And these are the most central people in the network. So the first one is Don Syme, who is the author of F#. This is the official Microsoft side of things account. This is the community account. And then Thomas had a talk yesterday. And Miguel de Casa, he's the author of GNOME and Mono. And I'm running this on Mono, so it works nicely. You can use it in various sorts of settings as well. I will skip this example because I wanted to tell you, like, for example, if in your company you communicate on Slack or whatever, you can also just use the information and see who replies to whom and create a social network out of that and see the communities of people. And you can do the same thing with email communications. And for example, email communication is a slightly different setting where all the links between people are oriented because someone sends other people an email. And it's another example where the degree doesn't really correlate with importance. Because, for example, a secretary that sends a lot of information emails is maybe not central in the social network. So we can use the same kind of analysis I did here. You can also analyze, for example, supply grids. If you have a blackout somewhere, how will that affect the rest of the network? And something I do most of the time is analyzing biological networks. For example, this is from a paper I was reading earlier this week, and they were looking at tumor suppressors and oncogenes in biological networks. And they found out that the genes that are actually important in development of cancer have high betweenness in protein interaction networks. It means if protein bind together, that means they have a link between themselves. And again, if we look at the network like this, oncogenes and tumor suppressors have higher betweenness. So it's really useful in the real world as well. And what I went through here was first, how to parse scripts, how to do data science, because I was calling functions from R using F#. And in data science, you have to do this a lot, because you have to combine languages, because there is never enough things in one language. I showed you some type providers. I explained some things in network science. But all this was using just a very small, fun data set on Star Wars. And I think it's really important to have fun with data sets like these. Because, for example, in the biological networks I analyzed, if a node has high betweenness, I don't really see why that happens. Or I may not have the clear intuition what that actually means, because the different nodes have different values and they represent genes or proteins. And it's really hard to interpret this, because I don't know all the genes in the human body. So if you play with something like this on a fun data set, you can immediately see what it means in terms of the story or in terms of this particular social network. And in a small project like this, I covered all these things. So it's very nice practice. And if you want to learn more, this is the website of the F# Foundation. So it has some guides how to start with F#. If you want to play with some networks, I recommend the iGraph package. I think it has some Python framework as well. If you want to look at the data I was showing here, You can look at the script. You can play with the API. I wrote 2 blog posts on this, and you can look at the Neo4j demo as well. This is how to follow me. You can follow me on Twitter. You can find me on GitHub. All the code will be on GitHub. And thank you.